Um, so on Monday, we were talking about this reaction where we add HX to a conjugated diene, and we showed how to get how you can use either one of those double bonds in that reaction um, and come out with these four different products. Uh, one of them we call the 1,2, and one of them the 1,4. And we left off talking about temperature, how the temperature affects the reaction. And we talked about this scenario where you start at the intermediate and then you have a basically a competition between the 1,2 and the 1,4 product. And at low temperatures, we said that this was irreversible. Right. And we also said that the kinetic product is just the product that's formed the fastest. Right. And so that's why once you make it, you're stuck. So even though it's a less stable product, which we have shown over here, is more accessible. Right. So low, when we do reactions at low temperature like this, we call this doing the reaction under kinetic conditions. All right. By the same token, if we did the reaction at a higher temperature and we started again at the intermediate, so I'm gonna copy this. If I can. So we're gonna run the reaction, but in this case, we're gonna do it at 37 degrees. So at 37 degrees, we're gonna expect the let me so that's the 1,4 product, and then this is 1,2 product. But at 37 degrees, we expect this product to be favored. All right, there's a reason for that. So unlike the kinetic conditions, at higher temperatures, we call this set of conditions, we say that we're working under thermodynamic conditions. Right, and you'll notice right here that it is the more stable product that is favored, right? If the energy diagram is is here, all right, and on the x-axis is time, and then on the y-axis is energy. Right, you can see that the 1,4 product is lower in energy. Right, so under thermodynamic conditions, the 1,4 product is going to be the favorite product. And also, if you notice, the activation barrier is higher, but so is the temperature. So if the temperature is higher, that means that there's more energy available to get over that activation barrier to get to the 1,4 product. Right, so the activation energy is not as much of an impediment in this case because the temperature is higher, so there's more energy available. So this is also under thermodynamic conditions, it's also reversible. So what you see under thermodynamic conditions with the equilibrium that's established, what you'll see is even the 1,2 product can revert back to the intermediate and then get converted into 1,4, right? So the less stable product can go back over the energy barrier back to the intermediate and then get converted into product. Right, so it can get converted back into the intermediate and then also get converted into the 1,4 product because the increase in temperature sets up an equilibrium. So you're able to go from the higher energy product, less stable product, back to the intermediate, and then get converted into the more stable product. All right. So these are the two sets of conditions. And this is why I think Tia brought this question up the other day about the temperature. And this is why the temperature actually matters, right? This is why it matters that when you do it at low temperature, you can control what product you get. And if you increase the temperature, you can also control what product you get. So at low temperature under kinetic conditions, the 1,2 product is usually favored. And then at higher temperatures, uh, when there's more energy available, you can get to that 1,4 product, which is your more stable product. All right. Go ahead, Tia.
So would the 1,4 product be like the one that you're trying to shoot for? Or does it just depend on the temperature that you're using?
Well, that's the beauty of doing synthesis. You get to pick. If you want the 1,4, run it at high temperatures. If you want the 1,2, put it on an ice bath and run it that way. But you get to pick that, and that's the beauty of doing organic synthesis is that many times you get to dictate the outcome of the reaction, even though you're always gonna get some side products and some competing reactions happening, but you get to pick that. Yeah, that's a great question. Um, any other questions about this? We're gonna go back and work through this other problem up here, dealing with this exact same. Let me cut this out. It's dealing with this exact same concept. All right, so let's work through this problem here. All right, it says if both products from the reaction done at 0, so both of your kinetic products, which we have up here, well, they're up there, but they're also drawn here. So this is kinetic, and that's the kinetic product from the second double bond reacting. It says that both products from the reaction done at 0 are warm to 40 degrees Celsius. So the product distribution changes, and the kinetic product is exactly what we were just talking about. The kinetic product is converted into the thermodynamic product. And it says using the major products from the reaction done at 0, which we already have drawn here, propose a mechanism for how this may occur. So let's think about that for a second. How would we go from the kinetic product? Let's start at the one at the top. How we go from that back to the intermediate? So look at what we have on the left, the kinetic product. Look at the intermediate on the right. How would you show that if I ask you to propose a mechanism for that?
Would you remove the bromine from the kinetic one?
Okay, how would you show it? I agree with that. You're just gonna pull it off, or do we need to put an arrow in showing it?
Put an arrow.
So we need
Yeah.
we need to show this bond, excuse me, breaking, right?
Yeah.
Hold up, that's too thick. We need to show this bond breaking like that. Is that right?
Yeah.
Where have we seen that before? Where we see a bromine or some other leaving group leave spontaneously? Have we seen that before anywhere before today? You know, that's a trick question because we have seen it. I'm just trying to see if you remember where we've seen it. Put some electrons in while we're waiting on them. Anybody? Wasn't this just on the last test?
It's substitution, right?
We've seen it with SN1, like a unimolecular type mechanism, right? SN1 and E1, where the leaving group leaves first. So the mechanism second. I'm trying to keep my palm off the screen. We've seen that. What makes this even more apt to doing so is the fact that when the leaving group or when bromine leaves, you're actually forming an allylic carbocation that can be stabilized by resonance, right? So we get to the intermediate through a SN1 type loss of bromine, right? Let me put that over here in parentheses. Right, because both SN1 and E1 involve the first step being the spontaneous loss of leaving group. All right, so now how do we go from the intermediate to the thermodynamic product? How would you show that part? And you can think about this, we talked about it the other day, you can think about it more than one way. You can think about it as the resonance product. So if you drew the resonance form, you would see where the plus charge would shift over, and that's where you would attack, or you can do it directly. It's up to you. But how would you show that?
So you like do the resonance and move the plus charge on the other side and move the double bond.
So
And then have the bromine.
go ahead.
Oh, and then I'll just have the bromine attack the positive charge on the left side.
So you want to do this first, right?
Because
So that's an allylic carbocation. So it's easy to shift the electrons over to here. And so the resonance form for that is going to look like this. right? Well, now the double bond is here. Sorry about that. That methyl group is still here, and the plus charge is here. Let me move that up some. Right, so that's good. So we can right, we can show resonance here. Sorry about that. And then follow that with just attack bromine on the plus charge to get to the thermodynamic product, right? And this is only possible because if you read the question, it's only possible because those reactions were warmed up to 40 degrees, right? And this is, if you think about doing this in a lab, and we have we're doing this reaction on this particular substrate, and let's just say, you set it up at -10, go to lunch and come back, but your cooling bath has warmed up to room temperature. More than likely, you're going to see a predominance of the 1,4 product. I mean, that's how this works. You have to keep it at that temperature until you're ready to quench the reaction and isolate your products. So if you're running it at 0 and you warm it up to 40, you do that with the expectation that the kinetic product is going to revert back to the intermediate and then get converted into the thermodynamic product. So let me put that over here. So your kinetic product can be converted into the thermodynamic product by increasing the temperature. Right. So anytime you're doing a reaction like this uh, addition of HX to a conjugated diene, and you have this competition, right? Depending on which product you want, you can determine that based on the conditions. All right, there's another aspect to this that I want to touch. And then after that, we're gonna push to actually push to another topic. Because the conjugated dienes, I think, precedes aromaticity, if I'm not mistaken. So yeah, let's go to, let's just look at another example of how we can apply this, right? So we can actually take a conjugated diene like this one. And let me just spice it up. Put methyl group here. And we can add like we can brominate it. Just like we add HX, we can add bromine. We can do all the same reactions that we learned in part 1 to a conjugated system. All right. The difference is that rather than going through a allylic carbocation, what happens when you do bromination? Anybody remember the mechanism for this? when you do a bromination reaction? Man, all these 8 students on here. Nobody remembers what happens here. What a shame. All right, let me
Isn't it like,
come on, come on.
like,
I knew I was gonna bring somebody out the woodwork with that comment. Come on.
like, propagation,
Mm.
uh,
No, this is not a radical reaction. You're thinking about taking bromine and doing radical substitution. This is different. If you recall, let me go. If you recall from part 1, you take a double bond, take an alkene, you treat it with Br2, you get a bromonium intermediate. So this is the intermediate plus Br minus. Is it coming back to you now? Like boomerang? And then this is going to attack here and pop that open. So the bromines are going to end up opposite to one another. That's a hallmark of this reaction, right? The bromines are anti to one another. Yes, no, maybe.
a little.
What a shame. What a shame. What a shame. All right. So this is a bromination. And the thing about it is that when you do this reaction on a conjugated diene, right, you're still going to get that same intermediate. So it's not going to be a carbocation. I mean, I'm sorry, an allylic carbocation. What you're going to get out is an intermediate that looks like this. Like that, right? This is going to be your intermediate. But the opening is going to happen at the allylic site, right? Because this is still the most valuable spot for a carbocation because it's going to be more stable because it's allylic. Right. So everything that happened in the initial reaction that we were looking at, as far as where the other bromine is going to attack, right, that's going to follow the same pathway. So again, this is another reaction that is going to follow all the same mechanistic rules that the addition of HX followed, right? Which means that if I do this at low temperature, right, where's that bromine going to attack if I do this at low temperature?
Second carbon.
It's going to attack where the highlighted carbon, right? If this is the alkene that gets brominated and we number these as 1, 2, 3, and 4, right? It 1, 2 attack is still going to predominate at low temperature, excuse me. So then I'm going to break that carbon bromine bond there. And then my product will look like this, where we have a bromine here. And then a bromine here. All right. Questions about that? What, so if that's the 1-2 attack, right? We can also think about 1-4 attack, where the bromine attacks at the other end. So let's do that. And let me show you. Uh-oh. Right. So then bromine can also attack here at the 4 position and shift that over. And that's still going to cause that carbon bromine bond to break. It's the same exact mechanism, it's just a different substrate. So my 1-4 product is going to look like this, where bromine is now here. And the other bromine is here. Right. And if we number the carbons, we'll see it's the same 1, 2, 3, 4, like that. Right. So you can actually do halogenations on these and get 1, 2, and 1-4 products. And they may seem trivial, but these are really important precursors to a lot of other compounds that you could build. These are building blocks for other compounds. All right. Questions about anything we talked about the thermodynamic control, kinetic control, and then this is all these halogenations are also either going to be thermodynamic or kinetic control based on the temperature. All right. Questions about that? All right. I'm going to give one more example. Right. Pause for a second. Draw the 2 products that you would get if this alkene was the one that reacted. Keep in mind up top too, both alkenes are equally susceptible to getting brominated. This is just one of the intermediates right here, right? There's another one that would look like this, where if the bromine was at the like that, right? This is the second possible intermediate. All right. So that's the other intermediate that's possible. But let's take a couple of minutes and I want you to draw the intermediate. If the double bond highlighted in purple is halogenated, and then also draw the two products. All right. And let me pause the recording because I know there's gonna be some dead air. First person to give me that, lunch is on me. I think, don't I still owe you lunch to you from the other day? You can go ahead and just annotate the screen. I'll put the answers
Okay.
in before I post the notes.
Okay. Well, can I just share my screen because I'm on my
All right, hold up.
thing?
Go ahead.
Oh, well, it was said I can't do it.
I turned it on.
It's not working. I think you have to
Oh
stop
yeah, I
sharing.
gotta stop. Yeah. Go ahead.
Okay. This is what I have.
Okay.
I don't know if that's right, but it's what I got.
No, that is my problem is for your 1-2 product, you have 1-2, right? But you're attacking at 1. You should attack at the allylic site.
Oh,
And I think you
oh,
have the right. Fortunately, you have the product itself is right, but the arrow and the mechanism should have been going from chlorine to carbon too. But the product is right though. You're going to get the same product either way, whether you attack at 2 or at 1. But the idea is that 2 is more susceptible to attack because it's allylic. So that carbon is a little bit more electropositive and a little bit more apt to accept a pair of electrons. So that's good. And then the 1-4, probably bet. So you get 2 lunches because I owe you lunch and then I gotta buy you lunch today.
you don't have to. It's fine.
All right, I know. I gotta keep my word though. But this is
Okay.
go ahead, Taj.
So like when she was drawing the carbocation or the cation mechanism, the intermediate, when she moved the double bond on the right side, how do you know like where to move the double bond to?
Good question. Can you put your screen back up to you?
Yes.
That's a great question, Taj, and a great way to end the class too. So you see where how you have those 4 atoms right in succession, where she has number 1, 2, 3, and 4. When you attack at 4, it's going to shift the double bond between 2 and 3. That's how you know where to put it. It's always going to shift it over to the next set of carbons.
Oh, okay, that makes sense.
Yeah. So it can't go anywhere else but there. Because once you attack at 4, if you don't break the double bond, 4 is going to have too many bonds to it. And the only place for it to go is to go between 2 and 3 because 2, because it's allylic and because it's also bonded to chlorine, it really has a really high partially positive charge. So with that, when you attack there, it's going to force the bond between carbon 2 and chlorine to break as well. So it's kind of like a cascade. Yeah, it's very well done. Go ahead.
I have a question. Did I number this right? Like the 1, 2, 3.
Yeah. That's
Okay.
the numbering is right.
Okay.
Yeah. All right. Any other questions? All right, we're gonna stop here. When we come back on Friday, we're gonna start aromatics, and I'll send you. So I'm gonna send you the videos from this topic, which I already sent, but you may or may not have watched them anyway. So I'm gonna send them again, and then I'll also send you a video dealing with aromatics, and the handout that you need for the next section is in assignments, uh, and it's I think it's either aromatics or aromaticity, one of the two. But there's one handout for this next section. There's not a lot of problems on there, but it's just more concepts. So we're gonna work through that, and then we'll take our next test probably either next Wednesday or next Friday. So we're gonna keep on trucking. All right, y'all have a great day, and see you back.